Good morning friends. Today we will going to discuss about the next constant K type of the filter, and inside this the constant K type of the filter there is a constant K high pass filter, and it's related to the solve examples on the constant K high pass filter. This is the prototype the constant K high pass filter. In case of the constant K high pass filter, just wait a minute. Here, in case of the constant K high pass filter, only the high frequency should be transmitted and the low frequency should be attenuated in the constant K high pass filter. A prototype T and pi high pass filter sections are as shown in the figure. From this diagram we have to draw here once again. The capacitor will be connected in the series arm just like this, and the inductor will be connected in the shunt arm impedance here. So that this is the series arm impedance and the shunt arm impedance, and here is the T section of the prototype T section of the high pass filter, where the capacitor will be connected in series. In case of the high pass filter, there is a 2C and here L. So this diagram should be indicated by a prototype T and pi high pass filter sections. So that here is the capacitor will be connected in the series arm impedance and the inductor will be connected in the shunt arm impedance. So that here capacitor 2C and L, and this is the pi section of the high pass filter, where capacitor is C and the inductor is the 2L and 2L respectively. Basically in the constant K high pass filter, only the high frequency, here high frequency should be able to transmit it, whereas low frequency will be attenuated. This is the cutoff frequency F of C. Means this is for just for your understanding purpose only. For the cutoff frequency, above the cutoff frequency slightly your frequency or your wave should be able to transmit it, and below the cutoff frequency where attenuation alpha which is equal to infinity. So that here is to attenuated it. The design impedance, while we have to be go through the any design parameters of the high pass filter, first parameter we always calculated or to design, which is called as the design impedance. Means in some book the design impedance will be in constant K, that's why it will be indicated by the R of K as well as R of 0. So that here basically the capacitor will be connected in the series arm impedance. There are the two capacitor will be connected in a series just like this here, and there is a inductor will be connected in the series arm impedance just like this. So that for this is the series arm impedance and here is the shunt arm impedance, and this will be represented by the Z of 1, and here shunt arm is represented by Z of 2. Means basically this is the 2C and here is the L. Based upon this diagram we have to be right now the total series arm impedance, and this total series arm impedance Z1 which is equal to minus J upon omega C. So that in case of the total shunt arm impedance, this is the shunt arm impedance, and in case of the shunt arm impedance the Z2 which is equal to J omega L. Then we know that for the constant K section the RK square which is equal to Z1 Z2 or R0 square which is equal to Z1 Z2. Then what we do here, whatever the total series arm impedance will be given, there is a Z1 and Z2, that will be substituted here. This equation will be substituted here. Then after substituting these all the equations in the design impedance R0 square which is equal to Z1 Z2, then the equation will be begins R0 square which is equal to minus J upon omega C into J omega L. Then what we do, the R0 square, which is equal to minus j upon omega c into j omega L. That's why this j and this j parameter should be get cancelled out, and once it will be square out, so that minus j square, then we know that the j which is equal to root of minus 1. Here we have taken root of minus 1, so that j which is equal to root of minus 1 will be taken into consideration, so that R0 square, which is equal to root of minus 1 into L upon C, and j square, which is equal to minus 1. That's why here is the equation about that j of square, which is equal to minus 1. So that this minus 1, and here is the minus sign, minus minus plus, therefore the equation will become R0 square, which is equal to L upon C. Therefore the R0, which is equal to root of L upon C, this is the design impedance of the band pass filter. This is the design impedance of the band pass filter. Okay, then what you do for the next parameter? The next parameter is related for the reactance curve. Then in the reactance curve, in this case the Z1, which is equal to minus j upon omega c, that's why x1 which is equal to minus 1 upon omega c, means the j omega c, that's why it is the x1. Then z2 which is equal to omega l, and x2 which is equal to omega L. Then the reactance curve of the frequency curve, reactance versus the frequency curve. This is the inductance, and this is the capacitance, and the both are the reactance of the parameter of the capacitor C and the inductor L. Then what we do here, the reactance versus the frequency curve of the x1 x2 x1 upon 4 and x1 upon 4 plus x2, that will be shown to the here. So here is the x2 and here is the x1. Here is the stop band should be occurred, and here is the pass band. Once the x1 is still goes on the increases towards the frequency, means frequencies goes on the increase, means definitely angular frequencies goes on the increases. Then x1 is goes on the decreases towards the positive value. That's why the point P and below the cutoff frequency it will be acting as the stop band, and above the cutoff frequency it will be acting as the pass band. So that here we have designed for high pass filter, means only the high frequency of the signal is allowed to pass through the output of the system. So from the reactance curve, expression of the cutoff frequency, and with the reference of the reactance curve, on the left of the point P, both the x1 by 4 and x1 by 4 plus x2 are on the same side of the frequency axis. Means here x1 by 4 and x1 by 4 plus x2 are on the same, here up to the here are on the same axis. But after the cutoff frequency, the x1 by 4 plus x2, this will be changes to the one axis to the another axis, means negative side to the positive side, and x1 will be remains on the same axis. So that with reference to the diagram, on the left of the point P, both the curve x1 by 4 and x1 by 4 plus x2 are on the same side of the frequency axis. So this gives the stop band, this gives the stop band. While on the right side of the point P, themselves curve on the opposite side of the frequency arm, so it will be gives the pass band. So what we do here, basically once this curve will be moving from one axis to the another axis, then your circuit will be changes from the stop band to the pass band, so that it will become to the pass band. So now the point at x1 by 4 plus x2 is the reactance curve crosses the frequency axis. So it will be give, once this parameter x1 by 4 plus x2, this parameter x1 by 4 plus x2, this is the reactance curve across the frequency axis. So it gives the value of the cutoff frequency omega c, and thus we can write x1 by 4 plus x2 which is equal to 0. Then what we do, basically x1 is the series, this is the reactance of the resistance, and x2 is the reactance of the inductance. So that x1 which is equal to minus 1 upon omega c and x2 which is equal to omega L. So what we do, therefore minus 1 upon 4 omega L plus omega L which is equal to 0. Then after substituting the value of the x1 to the here and x2 to the here in this equation, and rearranging the equation such a way that in this way, for this case, minus 1 upon 4 omega L plus omega L which is equal to 0. Then with rearranging the equation such a way that to find out the cutoff frequency, so that the cutoff frequency omega is replaced by the omega c. Whatever in the previous equation, the omega and omega which is equal to omega c. After substituting the omega which is equal to omega c, therefore the equation is minus 1 upon 4 omega c plus omega cl which is equal to 0. Then either you have to be do the one of the parameter will be changes from LHS to the RHS side and to rearranging the equation. So what we do here, better way, minus 1 upon 4 omega c, this parameter will become on the RHS side. And once this parameter will become on the RHS side, therefore this equation begins the omega cl which is equal to 1 upon 4 omega c into c. That's why the rearranging the equation, omega c square means this omega c and omega c square which is equal to 1 upon 4 lc. Therefore take the square root on the both side. After taking the square root on the both side, the omega c which is equal to 1 upon 2 root of lc, means square root of 4 is the 2 and here is the root of the lc. So that this equation will be begins here omega c which is equal to 1 upon 2 root of lc. Then what we do, the omega which is equal to 2 pi f, means here is omega which is equal to 2 pi f. We know that this basic equation, omega which is equal to 2 pi f, and the omega is replaced by omega c, therefore omega of c which is equal to 2 pi fc. Here is the 2 pi fc. fc means omega c which is equal to 2 pi fc, and this value will be substituted to the here. So what we do, 2 pi fc which is equal to 1 upon 2 lc and 2 to 4 pi. That's why here is the 4 pi square root of lc. Therefore your cutoff frequency fc which is equal to 1 upon 4 pi root of lc. In this way we have to be find out the cutoff frequency of the band pass high pass filter. Then for the T section we have the ZOT which is equal to, we know ZOT which is equal to Z1 square upon 4 plus Z1 Z2. Then what we do in case of the T section, we substitute the value of the Z1 and Z2 in this equation, so that here the ZOT which is equal to root of Z1 square upon 4 plus Z1 Z2. And after putting the equation, the impedance of the T network is the square root of plus Z1 square means J square, actually J which is equal to root of minus 1, okay, and Z1 square which is equal to minus J square, and J square which is equal to minus 1, and that minus 1 plus 1. That's why here is the plus J square upon 4 omega square C square plus Z1 is minus J upon omega C and J omega L. So what we do here for this case, here omega and omega gets cancelled out, and J which is equal to J square which is equal to root of minus 1 j which is equal to root of minus 1 and j square which is equal to minus 1, and this minus minus plus. So again the equation will be begins here, means basically here j square means j which is equal to root of minus 1, you clear here root of minus 1, and if j square which is equal to minus 1, that's why this parameter will become to the here minus 1 upon 4 omega square c square plus L upon c. Hence the equation will be begins here root of LC. This equation is come root of means L upon c minus 1 upon 4 omega square c square. Say then after that the root of L upon c will be taken as a common. Then root of LC which is equal to design impedance R0. So the finally the impedance of the T network in the high pass filter will be given as ZOT which is equal to R0 root of 1 minus 1 upon 4 omega square LC. Then we move towards the from equation we conclude that the ZOT is the real or imaginary. If this value should be less than 1, then it is real, and if this value should be greater than 1, then it is imaginary. Thus the condition will be 1 minus means in the previous equation 1 minus means this parameter 1 minus 1 upon 4 omega square LC. This equation will be taken as to find out the cutoff frequency. So how to find out? See here. 1 minus 1 upon 4 omega square LC which is equal to 0. That will be gives the equation of the cutoff frequency. So we have to be find out the cutoff frequency. There is some assumptions we have seen in my previous video. There is angular frequency omega which is equal to omega c. So that 1 minus 1 upon 4 omega c square LC which is equal to 0. Then what you do, you have to be think about it. Once you have to be think it, then this parameter means this parameter you want to move towards the LHS to the RHS side, means the sign will be definitely changed from minus to plus, and rearranging the equation such a way that 1 upon 4 omega c square LC which is equal to 1. Therefore omega c square which is equal to 1 upon 4 LC. Therefore here omega c, then what will you do? Our aim is to be find out the cutoff frequency in the high pass filter. So that omega c square which is equal to for T network, specifically for the T network, so 1 upon 4 LC, and take the square root on the both sides. That's why the omega c which is equal to 1 upon 2 square root of LC. So omega c which is equal to 2 pi fc. That's why fc which is equal to 2 pi into 2 means 4 pi under root of LC. In this way we have to be find out the cutoff frequency fc which is equal to 1 upon 4 pi LC. Then you keep in mind this cutoff frequency is basically 1 upon 4 pi LC, and here is the 1 upon 4 pi LC. Both the equations should be equal. Then variation of the ZOT and ZO pi with the frequency. Then we know that the ZOT which is equal to R0 square root of 1 minus 4 omega square LC, and omega c square which is equal to 1 upon 4 LC. Means 1 upon 4 LC means this 1 upon 4 LC, this parameter, and this parameter will be again represented here. There is a R0 square root of 1 minus 1 upon 4 LC which is equal to omega c square, means here omega c bracket raised to square upon omega square, means this is the omega square. Means the equation will be same come to the here. The ZOT which is equal to means ZOT and ZO pi with the frequency. That's why ZOT which is equal to R0 under root of 1 minus omega c square upon omega square, which is equal to r0 under root, then omega which is equal to 2 pi f, that's why 2 pi f c upon 2 pi f, that's why this equation is which is equal to r0 under root of here 1 minus 2 pi fc, means here is the 2 pi f of c here upon here is the 2 pi f. F and its square. So what we do here is the 2 pi and 2 pi gets cancelled out and only fc upon f, this term will be remains as it is. That's why the equation is a root of 1 minus fc upon f bracket raised to square. So as the frequency increases from fc to infinity in the pass band, and ZOT is increases from 0 to R0, means design impedance. Now ZO pi is related to the ZOT, that's why ZO pi which is equal to Z1 Z2 upon ZOT. Then from that equation what we do, the Z1 Z2 which is equal to R0 square, and putting this equation 30 into the 31, that's why ZO pi which is equal to R0 square upon R0 root of 1 minus fc upon f. Then this R0 and this square gets cancelled out and the term will be remaining the ZO pi which is equal to R0 upon root of 1 minus fc upon f square. As the frequency increases from fc to the infinity, the ZOT is a decreases, means this parameter should be goes on the increases, means definitely ZO pi is the decreases. And as the frequency f is increases from fc to infinity, ZO pi is a decreases from infinity to R0. Here is from ZO pi is a decreases from infinity to the R0. And after the cutoff frequency, your ZOT should be goes on the increases from fc to R0, fc to the